Now we will present our second application, inhibitor leaching performance from coating matrix. Katja Schladitz and Helena Zaninovic from Fraunhofer Institute of Industrial Mathematics will provide this presentation. Katja, Helena, floor is yours.
So I will start with a short presentation on the ideas behind the app, and then we'll hand over to Helena, who will show how it exactly works. I start with my short presentation. The idea of App2 is to describe the inhibitor delivery on the micro scale. And this is the result of joint work with a lot of people from the VIPCOAT consortium. I just mentioned here the people who are really involved in developing the app. So this is Peter Klein and Tim Tassone and Michael Godehart, all from ITWM. The idea behind App2 is microstructure optimization. What do we mean by that? We want to observe the real microstructure, in our case, the inhibitor particle distribution, meaning their sizes, their shapes, and how they are placed within the coating sample. We want to derive geometric features of these inhibitor particles, then use these observed features of the real pigments to build a stochastic model capturing as much of their geometry as possible. And within realizations of these geometric models, we can then later on simulate the diffusion process leading to the leaching. And finally, that would enable an optimization of the microstructure in the sense that you can change the microstructure such that the leaching process is faster, longer, whatever you're aiming at. Currently, the app covers just the geometry generation part, but behind that is the observation of many, many pigment systems. We started off with nearly real samples having 3 different inhibitor particles plus titanium dioxide, but then realized in order to really observe them in 3D and to derive the needed geometric characteristics, that was a bit too complex. So we reduced later on to 1 to 2 pigment types, and we left out the titanium dioxide, which improved image quality a lot. Altogether, we have 250 reconstructed 3D images, each about 1,000 cube voxels, and we have observed them dry, and after several times of leaching, of being exposed to water, we also have in situ observations. So there's a lot of imaging, experiment, and image analysis behind what we actually do now in App2. So we have measured at the German Synchrotron in Hamburg at DESI and gained micro and nano CT images at several contrast modes. For feeding geometry generation, we only use the nano CT images, and their phase contrast as well as absorption contrast as well as holotomography. Details about how we got the geometric features from these images are described in the paper mentioned on the bottom of the slide. So we got geometries, and we also were able to fit a very complex geometry model to that. For the app, however, we decided to go for simpler geometries, namely cuboids for the pigments, in order to generate the geometries faster. So the user can now choose how big the observation window is that he or she wants to use and fill with the pigment particles. The user can also choose the resolution, the voxel edge length, and then the target pigment volume concentration, which shouldn't be too high in order to get a reasonably fast answer. Then size distribution, meaning the mean and the standard deviation of the radius of the equal volume sphere, and a pigment shape type, either a platelet or a rod. And if you choose that the aspect ratio is just 1, then you get cubes as well. And there are some chemical parameters with placeholders for later use. And I also show you some typical outputs. The renderings of two realizations that you can see here are also shown to the user to be able to decide whether the geometry should be kept or discarded and a new one should be generated. And here are results showing the variability of the geometries that we can generate right now. At the example of calcium sulfate, on the top row you see variation of the shape, platelets, cubes, or rod-like lengthy pigments, and on the bottom you see variations of the particle volume fraction. So thank you for your attention for this background information.
So let's get it running to save a bit on time. So what we're trying to do here is we're generating a synthetic coating. The first two parameters here determine the size of the chunk of the coating that we want to look at. And then the next parameter is the target volume density, or rather the pigment volume concentration, or how densely these pigments are packed in this chunk. And then we have two variables that can influence the size distribution of the pigments, and finally two variables that determine the shape distribution. For example, here I'm going for a long particle, so most of them are still going to stay very cube-like, but if they deviate from this like cube shape, they're going to be elongated, rod-like. However, not so much, because I chose a smaller standard deviation, so most of them are going to look like cubes. So here you can see one example, like one realization that satisfies our input. I will now run the model a second time to show you how different it can look. So let's decrease this. Let's change the deviation, and this time we'll go for a different shape. So this time I changed the pigment so that you'll see what it looks like when they tend towards a flat shape, when they are more flaky. Of course, based on which parameters you change and how you change them, you can increase or decrease the execution time. So for example, if I generate a larger chunk, of course, it's going to take a little longer. If I choose a higher pigment volume concentration or this volume density, of course, it's going to be much more challenging to pack them all in and satisfy the other requirements, so it's also going to take longer. And of course, if I choose wilder sizes and shapes, then that might take more time as well. So here you can see a realization that is much less densely packed than the first one, and you can see that most of them are still cube-like, but you have plenty of these flat platelet shapes. So of course, you can influence you can change the parameters to suit your like target. You can change the distribution, the size distribution, the shape distribution. The parameters that I use now are based on real information that we got from analyzing actual coding samples. So this is roughly what they actually do look like. That is it from my side. I'll stop.
Thank you very much, yeah, Katja and Helena. And we are looking forward to see the application at the OIP. Thank you very much.